Welcome, class. Today's explainer jumps straight into a cosmic mystery. We're going to explore how the microscopic rules of physics, specifically how light moves through objects, scale up to explain the macroscopic mechanics of solar and lunar eclipses. Let's get right into it. It might seem a bit counterintuitive to begin an explainer about massive planetary bodies by looking at things on a microscopic level. But to understand the darkness of an eclipse, we first have to understand light. Specifically, how does the microscopic jiggling of atoms on the surface of a material connect directly to the temporary disappearance of the sun in our sky? Section 1. How light interacts.
Before we look up at the shadows cast in space, we have to establish the basic rules right here on Earth. When light travels and hits a material, a few things can happen. The first is absorption. Light is absorbed by a material if the frequency of the incoming light wave is near what we call a resonant frequency, which is simply a frequency characteristic of that specific material. Think of resonant frequency like a highly specific lock and key. If the incoming light wave perfectly matches the atomic energy levels of the object, the lock turns and the material absorbs the light.
Now, when this absorption occurs, the energy from the light doesn't just vanish. It converts into vibrational energy. Simply put, it causes a literal jiggling of the atoms within the material, and we experience this microscopic jiggling on a macro level as heat. So when you step outside and soak up the sunlight your skin absorbs excites a resonance. It increases the vibrational energy of the molecules in your skin, and you heat up.
The second major behavior of light we need to understand is reflection. When light reaches an interface, which is really just a boundary between two different mediums, like air meeting water or light hitting a mirror, some of that light wave will bounce off the surface instead of being absorbed. The physical properties of those two mediums determine the intensity and the frequency of that reflected light.
The most critical rule governing this behavior is the law of reflection. This law simply states that the angle of incidence, meaning the angle at which the incoming light strikes the boundary, is exactly equal to the angle of reflection, the angle at which it bounces off. It's a perfect, predictable geometric mirror effect that remains absolutely consistent across all of physics. So the crucial takeaway here is that our everyday visual experience is governed by a combination of absorption and reflection. The objects and colors we see all around us are entirely determined by which specific frequencies of light are absorbed by a material and converted into heat, and which frequencies bounce off the boundary and are reflected back into our eyes. But what happens when the material doesn't just absorb a specific color, but blocks the light entirely?
Section 2. When objects block light. Materials can generally be transparent, letting light pass through, or they can be opaque. Opaque objects are dense enough that they completely block the transmission of light. Because the light waves cannot pass through, pass around, or completely reflect away in all directions, an area of darkness is cast behind the object. And this absence of light is exactly what we call a shadow.
Shadows, however, aren't just uniform blocks of darkness. They actually have specific anatomical structures. I want you to picture the very center of a shadow, the darkest, deepest part. In physics, we call this the umbra. The umbra is the inner, cone-shaped part of a shadow, where absolutely all of the direct light from the source has been blocked by the opaque object. Zero light makes it past this point.
Framing that deep, dark center is a secondary region known as the penumbra. The penumbra is the outer part of a shadow where only a portion of the light source is blocked. I'll restate that to ensure it's completely clear. In the penumbra, the light is merely dimmed, not totally absent. If you were to stand in a penumbra, you would still see a piece of the light source peeking past the opaque object. With a firm grasp on opaque objects, umbras, and penumbras, we're now ready to scale these microscopic rules up to the staggering size of our solar system.
Section 3. The solar eclipse.
A planet or moon is, fundamentally, just a giant opaque object. Because the laws of physics are universal, the exact same mechanics of the umbra and penumbra apply when these massive bodies interact with sunlight in the vacuum of space. The Earth and the Moon are constantly casting massive, cone-shaped shadows out into the solar system. And this brilliantly illustrates the mechanics of a solar eclipse. A solar eclipse occurs when the Moon, acting as our opaque object, passes directly between the Earth and the Sun. As it does this, the Sun is either partially or totally hidden from our view. The Moon literally drags its shadow across the surface of the Earth. If you're standing in the Moon's tiny umbra, you experience a total eclipse. If you're in the wider penumbra, you see a partial eclipse. So we've seen what happens when the Moon blocks the light. Now let's reverse the celestial roles.
Section 4. The lunar eclipse.
A lunar eclipse is governed by strict celestial geometry. For this to happen, the Earth must sit perfectly between the Sun and the Moon. Furthermore, this can only occur during a full moon phase. And crucially, all three bodies must line up in the exact same mathematical plane, which we call the ecliptic. Imagine a giant flat sheet of glass cutting through the center of the Sun and Earth. The Moon must cross exactly onto that flat sheet for an eclipse to happen. Because orbits are slightly tilted, they don't perfectly align every month, which is exactly why we don't see eclipses constantly.
Let's see how this event builds sequentially. As the full moon moves along its orbit, it first slides into the Earth's penumbra. Here, the sunlight reflecting off the moon merely dims. It's a very subtle change. But as the orbit continues, the moon plunges deeply into the Earth's umbra. In this inner, cone-shaped shadow, the direct sunlight is fully blocked from hitting the lunar surface, completing the eclipse.
We've covered a lot of ground today, from the tiny jiggling of atoms on your skin as they absorb specific frequencies of light, to the massive shadows cast by planets operating under those exact same principles. The rules of physics remain beautifully consistent regardless of scale. And it leaves us with a compelling thought. If we can decode the mechanics of the universe just by observing how a simple opaque object casts a shadow, what other cosmic mysteries might we solve just by watching the dark? Thank you for your focus today, class. Keep questioning what you see.